training a diffusion model and asking, will it dream up something new or just spit back what it memorized? This paper tackles that puzzle head-on. Instead of hand-wavy guesses, the authors build a mathematical playground where they can watch models flip from generalizing to memorizing. The key idea is a crossover point. Below it, the model generates fresh-looking samples. Above it, it starts copying the training data. And here's the kicker. They show this phase transition happens right around 80% of the dataset size. By treating diffusion models like a science experiment, they turn fuzzy debates about creativity and memorization into clear, predictable math. In today's deep dive, we'll unpack how they set up this laboratory, what the crossover really means, and why this matters for everything from copyright to the future of generative AI.
All right, let's dive into this paper. The abstract kicks things off by questioning when diffusion models, which are all the rage in AI for generating images and more, stick to what they know, reproducing training data, and when they venture into new, uncharted territory. This isn't just an academic puzzle, it's a big deal for real-world applications. Think copyright and privacy issues when models memorize too much. The authors propose a neat way to explore this memory retention versus broad learning battle. They set up a sort of scientific playground, using synthetic and structured image data to tease apart these concepts. They've got this idea that the behavior of a model, whether it retains memory or learns broadly, is really about the training loss. It's like comparing two scenarios, one where the model remembers everything versus one where it learns broadly. To put this to the test, they look at a transition point. This is where the training loss of a model that learns broadly overtakes that of a model that just retains memory. They back up their theory with experiments, tracking how this transition point predicts when a model shifts from broad learning to memory retention. It's like finding the tipping point in model size where memorization takes over. Moving into the introduction, we get a sense of why diffusion models are exciting. They're powerhouses in generating realistic images, videos, and even protein structures. But there's a catch. These models can sometimes memorize data, leading to privacy and copyright headaches. The paper points out that distinguishing between memory retention and broad learning isn't easy, and highlights the ongoing research efforts to tackle this. Here, we delve deeper into the theoretical groundwork for understanding memory retention in diffusion models. The authors highlight the challenges of current ad hoc methods that examine how features from a model's encoder compare to training data. This isn't just theoretical, it has real-world implications for legal and ethical issues around AI-generated content. They aim to create a more robust framework to understand why well-trained models sometimes retain memory and other times don't. They introduce a unique setting called a memory retention laboratory to explore this. It's not a physical space, but a conceptual framework using synthetic data to understand how models learn and retain memory. They hypothesize that whether a model retains memory or learns broadly can hinge on the training loss, especially in models that use gradient descent. They speculate that this loss can be lower for models that retain memory versus those that learn broadly. In this controlled setting, they introduce a partially retaining noise filter model. This model helps pinpoint the transition point where a model shifts from broad learning to retaining memory. The idea is to predict when this shift happens, allowing for better control over model behavior. They acknowledge the complexity involved in training diffusion models, especially with natural images. This framework is designed to be manageable while capturing the essential dynamics of memory retention and broad learning. Now let's get into the technical heart of diffusion models. These models aim to approximate a target distribution. Imagine you're trying to map a complex landscape using only rough sketches. That's what diffusion models do with data, using a process that adds noise to create an output distribution. The key here is the noising process, which is mathematically detailed. It's like adding layers of fog over a clear image. Look at the way they describe reversing this fogging, retrieving the original data, peeling back layers to reveal the clear picture underneath. To make these models practical, there's a focus on minimizing the training loss. They discuss a method to adjust the model so it approximates the target distribution as closely as possible. They introduce a memory-retaining noise filter, a model that gets really good at recalling the training data. Finally, they touch on how data itself is structured using a Gaussian mixture model. Think of this as mixing different types of fog to create a particular atmosphere. This mixture helps represent a wide range of datasets, making the analysis flexible and applicable to various scenarios. Diving deeper, let's explore how Gauss-Clearian mixture models clarify diffusion models. The authors present a proposition that describes how a noise filter works within this framework. Imagine a noise filter as a filter that processes noisy data to retrieve clean information. The equation they provide breaks down how this filter weighs different data components to make predictions. Then, they tackle a critical question. How do we determine if a model retains memory or learns broadly? They introduce a definition to measure memory retention. It checks if the model's outputs match the training data or the intended target distribution. It's like checking if a student is reciting facts or genuinely understanding the material. They also highlight the importance of sample size in this determination. As the number of samples scales up, the difference between memory retention and broad learning becomes harder to pin down. They use a mathematical distance measure to argue this point, suggesting that, in high dimensions, these behaviors can become indistinguishable. Now let's tackle the core question. When do diffusion models retain memory, and when do they learn broadly? Here, tables clarify key terms and parameters, like the number of samples and model capacity. These are the building blocks of their investigation. They introduce surrogate noise filters, simplified models to help predict the behavior of more complex ones. Imagine these as practice runs, giving insights into how real models might behave. The goal is to understand how these models transition from retaining memory to learning broadly. The authors propose an assumption focusing on training losses, suggesting that understanding these losses can help predict when a model will retain memory. This involves comparing different noise filters and examining their performance. Next, check out the formulas depicting how these noise filters are structured. One formula shows how a memory-retaining noise filter handles data, while another shows a broad learning noise filters approach. These equations help us understand the conditions under which a model might switch from retaining memory to learning broadly. Let's dive into the nitty-gritty of training losses for memory-retaining and broad learning noise filters. The authors compare these losses to understand different model behaviors. They use high-dimensional math to predict training losses, aiming to see how well these predictions match real-world outcomes. Look at Figure 1 here. It visually shows how the predicted training losses align beautifully with reality. This graph compares a broad learning noise filter with one that tends to retain memory, highlighting how close these predictions are to real outcomes. The page also introduces Rule 3.1, a mathematical deep dive into expected training loss. It explores how factors like the signal-to-noise ratio and model parameters impact this loss. The rule provides a precise way to measure how these elements play out as models scale up in complexity. Finally, the formulas express the objective of minimizing this training loss, breaking it down into understandable components. This helps us grasp how models transition between retaining specific data and learning new, unseen information. Now let's tackle some heavier math with Rule 3.2, which dives into the expected training loss for noise filters that partially retain memory. The rule gives us a formula showing how this loss behaves as data complexity increases. It's like a roadmap predicting performance as models get more complicated. Next, there's a comparison of when different noise filters have lower training losses. Here comes the transition point, a critical threshold where one model type starts outperforming another. This is crucial for understanding when a model shifts from learning new information to just retaining old data. We then move to experiments, where theory meets practice. They talk about how their laboratory setting can predict when models make this shift from broad learning to memory retention. The experiments validate these theories, showing that models indeed go through this transition and even provide a predictive model for it. Let's explore the fascinating phase transition from broad learning to memory retention in diffusion models. Look at Figure 2 here, showing how models shift from generating new insights to simply retaining memory as their complexity increases. The plots reveal changes in memory retention ratio, training loss, and test loss, painting a visual story of this transition. The authors illustrate that as model size grows, it starts retaining nearly all the data. This observation aligns with prior studies, cementing the idea that larger models tend to retain more memory. Check out Figure 3 next, highlighting how we can predict this phase transition using only approximate training losses. It's like having a weather forecast telling us when a model will switch behaviors. To find the exact point of transition, the authors describe an optimization problem. This involves calculating a specific weight that marks the transition point for memory retention. The whole idea is to pinpoint when a model stops learning new patterns and starts repeating known ones. Let's bridge theory and real-world application using visual examples. Look at Figure 4 here, presenting synthetic images from a simple model alongside their single-color templates. This helps us see how the model can mimic natural image distributions using simpler structures. The text dives into pinpointing the transition point the moment a model transitions from broad learning to memory retention. The formula for this involves finding the model size where this transition happens, using a specific weighting of loss. This mathematical approach ensures the predictive model remains accurate, allowing us to forecast when a model will start to retain memory instead of learning new patterns. They also introduce experiments with a simple image model using a Gaussian mixture framework. This setup replicates the behavior of natural images, making it possible to study these transitions in a controlled environment. The authors emphasize that their framework is robust enough to handle complex image distributions and replicate phenomena seen in real-world data. Finally, the related work section underscores the importance of understanding memory retention and broad learning, touching on privacy and copyright issues that these models must navigate. Finally, let's delve into a visual and theoretical exploration of phase transitions in diffusion models. Look at Figure 5, which shows how, as the number of components in a model increases, it transitions from broad learning to memory retention. The memory retention ratio, training loss, and test loss are plotted to demonstrate this shift clearly. The discussion shifts to the theoretical side, where the authors explore how these transitions are studied through the concept of phase transitions. They reference previous work on these shifts, especially within Gauss-Carrian models, providing a broader context for understanding model behavior. In the conclusion, the authors recap their introduction of a theoretical laboratory designed to measure and predict when models retain memory versus when they learn broadly. This laboratory uses Gaussian mixture models and noise filters to dissect the factors that influence these behaviors. The aim is to predict precisely when a model will start retaining memory. They also outline future directions, suggesting that the current framework could be expanded to handle more complex datasets and refine their models further. This laboratory could eventually provide a robust framework for testing and predicting model behavior, offering a deeper understanding of the geometry of data. Thanks for joining us today. Happy exploring together!